Hello, and welcome back to our Living Climate presented by the My Name is Climate Foundation. In our last chapter, we followed the incredible journey of energy from the sun. Now, we explore what happens when it gets here. We now begin Chapter 2, The Earth's Energy Budget, a Delicate Balance. Section 2.1, The Great Arrival.
In the last chapter, we followed an incredible journey, a torrent of energy, born in the nuclear furnace of the sun's core, traveling across 93 million miles of empty space to greet our planet. This constant stream of solar radiation is the ultimate income for our world. But what happens when this cosmic payment arrives? It's tempting to think of Earth as a simple recipient, a cold object that just soaks up the sun's warmth. The reality is far more dynamic. The Earth system, its atmosphere, clouds, oceans, ice, and land immediately begins to interact with this incoming energy. Some is accepted, some is rejected, and all of it is eventually accounted for. To understand how Earth maintains a relatively stable temperature over millennia, we can think of it like a household budget or a bank account. There are energy deposits income and energy withdrawals expenses. For the planet's temperature to remain balanced, the budget must balance. The energy coming in must equal the energy going out. This is the Earth's energy budget, and it is the single most important concept for understanding our climate. Let's break down the transactions.
Section 2.2, The First Transaction, Immediate Rejection, Albedo.
Before most of the sun's energy even has a chance to warm the ground, a significant portion is immediately reflected and scattered straight back into space. This is Earth's first line of defense against overheating. The scientific term for this reflectivity is albedo, from the Latin word albus, meaning white. Albedo is simply a measure of how much light a surface reflects. A surface with a high albedo is highly reflective, like a mirror, while a surface with a low albedo is highly absorbent, like black velvet. Think about wearing a black t-shirt versus a white t-shirt on a hot sunny day. The black shirt absorbs more sunlight and gets much warmer, while the white shirt reflects more sunlight and keeps you cooler. The Earth's surfaces work in exactly the same way high albedo surfaces. Bright, pale surfaces are the planet's mirrors. Fresh snow and thick ice are the champions of reflectivity, bouncing as much as 80 to 90% of the sun's energy back into space. Bright, thick clouds are also excellent reflectors, which is why a cloudy day can feel so much cooler than a clear one, even in summer. Deserts and dry soils also have a relatively high albedo. Low albedo surfaces. Dark surfaces are the planet's sponges for energy. The deep blue of the open ocean is one of the least reflective surfaces on Earth, absorbing over 90% of the sunlight that hits it. Dark green forests, rich soils, and human-made surfaces like asphalt also have a very low albedo, soaking up energy and heating up. On a global average, when you combine the effect of clouds, ice, oceans, and land, Earth reflects about 30% of the incoming solar radiation back to space. This 30% does nothing to warm the planet. It's an immediate rejection, an energy deposit returned before it ever enters the account.
Section 2.3, The Second Transaction, Absorption.
What happens to the remaining 70% of the solar energy that isn't reflected? It is absorbed by the Earth system, representing the main income in our energy budget. This absorption is what warms our planet. The energy is absorbed by three main components. The atmosphere, a small portion, about 23% of the total, is absorbed directly by gases, dust, and water vapor within the atmosphere as the sunlight passes through. The land surface. Continents, rocks, and soils absorb sunlight, causing the ground to heat up. You can feel this effect when you walk barefoot on a sandy beach or pavement on a sunny day. The oceans. As the largest and darkest feature on our planet's surface, the oceans absorb the most solar energy of all. This process is key. The sun doesn't primarily heat the air directly. It heats the surface, the land, and the water. This warmed surface then heats the layer of air directly above it, a bit like a stove burner heating the air in a kitchen. This is a crucial distinction that will become even more important as our story unfolds.
Section 2.4, Balancing the Books, Radiating Heat Out.
So far, we have a budget with a steady income, the 70% of solar energy that is absorbed. But if that were the whole story, Earth would have a serious problem. With constant deposits and no withdrawals, the account balance would rise indefinitely, and the planet would get hotter and hotter until it boiled. To balance the budget, Earth must have an expense column. It must constantly lose energy back to space. It does this by radiating energy away. Everything in the universe that has a temperature above absolute zero radiates energy, including you, this book, and the entire planet. Here is the most critical piece of the puzzle. The incoming energy from the sun is mostly high-energy, short-wave radiation, like visible and UV light. The outgoing energy radiated by the much cooler Earth is lower-energy, long-wave radiation, which we know as infrared radiation, or simply heat. For Earth's global average temperature to remain stable, the amount of energy it absorbs must be equal to the amount of heat it radiates